Some special types of sequences. For our first type, we have arithmetic sequences. So what are we going to do? We're going to start with an A number B, and then A sub n is going to be defined by, you take your A, and then you add n multiples of B. So let's try A sub n equal to 1 minus 3n. So here, A is 1, B is equal to minus 3. So let's run out the first few terms. So if I put a 0 in for n, we're going to get 1. If I put a 1 in for n, we're going to get 1 minus 3, which is minus 2. I put a 2 in, it's 1 minus 6 is minus 5. And then what you'll notice, the pattern that's coming out of this is to go from one term to the next, all we need to do is subtract 3. Okay, we can turn this into a recursively defined sequence. If I note, we're going to start with a0 equal to 1, and then the way I get to my next term, so I get my a sub n by just taking the term that's before it, and then we just add minus 3 or subtract 3. So that's what's happening here. To get from 1 to minus 2, I subtract 3. To get from minus 2 to 5, I subtract 3, and so on. If we want to look at a picture of this, then our arithmetic sequences are going to look like basically a bunch of dots that live on a straight line. So here it's going to start at 1, and then we'll note the next point's a minus 2, and then you just connect the dots, or unconnect them as the case may be. Okay, try another one. A sub n equal to 0.5 plus 0.01n. So the idea here is you don't have to always use your integers for a and b. They can be any numbers, pi, pick your favorite, square root of 2. So if I put in a 0, I'm going to get a 0.5. I put in a 1, we're going to get 0.51. Put in a 2, we get 0.52. So you notice the way I go from one term to the next is just by adding 0.01. Okay, and then that tells us how to define things recursively. I'm going to start with a0 is 0.5, and the way I go from one term to the next is just to add 0.01. So it's the equation a sub n equal to a sub n minus 1 plus 0.01. Okay, if we were to draw a picture, it would be a line that starts at 0.5, and then this one would be going up. So it would have a line with positive slope. Okay, the next type, these are going to be very important for what comes later on. These are going to be geometric sequences. So the idea here is you're going to pick a number r, and what we're going to do is we're just going to keep raising that number to higher and higher powers. We'll also have another number a out in front in case we want to just do some extra multiplication. Anyway, you'll see what I mean by that. So for instance, let's take a sub n equal to 2 times 3 to the nth power. So let's see. If I put a 0 in, 3 to the 0 is 1, so I get a 2. If I put a 1 in, this is 2 times 3, which is 6. I put a 2 in, this is 2 times 9, which is 18, and so on and so on. So what's the rule going to be? To go from one term to the next, all I have to do is multiply by 3. Okay, so again, we're going to have a recursive definition for this. I start at a0 equal to 2, and then, like I just said, the way I go from one term to the next is just to multiply by 3. If we look at the graph, well, this thing's going to spike up really hard, so it's going to look sort of like, in this case, 3 to the n, and then we just scale it by 2. So remember, 3 to the n, you get that by plotting 3 points, and there's a horizontal asymptote back here. Let's try same type of geometric sequence, only now we'll flip the 3 over. So I'm looking at a sub n equal to 2 to the 1/3 to the nth power. So what do we have here? Same idea. I put 0 in, we get 2. Put 1 in, now we're going to get 2/3. Put 2 in, I get 2/9. 3 in, I get 2/27, and so on. So you'll notice as I go from one term to the next, we're going to multiply by 1/3. So that's going to let me define things recursively instead as a sub 0 is equal to 2, and then the way I go from one term to the next is just to multiply by 1/3. The picture for this, we start at 2, then we're going to go to 2/3, and you'll notice this thing, as we keep multiplying by 1/3, is getting driven closer and closer down to 0 as we go out in that direction.